The influence of a great teacher reaches well beyond the classroom, often lasting a lifetime. The best teachers teach from the heart, and not just from a textbook or chalkboard. Dr. Rishi Gupta has dedicated his career to guiding the next generation of engineers, combining theory and practice in a way that truly connects with his students.
My mantra for many years actually has been that we need to have problems that are the real world, and what better than asking those questions to the industry professionals. I engage industry sponsors or partners right from the beginning. So the question gets asked to industry sponsors to say, what is it that's bothering you? What is it that you want to solve? And we use that as project topics for the students.
Rishi joined the civil engineering program at the University of Victoria as one of its first hires and brought with him a wealth of engineering and teaching experience. His efforts were quickly recognized as he received some of the highest teacher ratings in the faculty and was presented with the faculty's Teaching Excellence Award in 2015. He has served as the director of the undergraduate program in civil engineering since 2016.
One of the things that I've tried to do is have many undergrad students hired within my research lab. So it's not just fundamental research, but something that's applied and get used in the field.
Dr. Gupta had a very great teaching style. I would never forget his class. It was second year civil engineering materials, where we had a lot of time in the lab, a lot of hands-on experience there. It was an experience I'll never forget.
He is recognized across the nation as a leader in academia, inspiring young minds to reach for more and continually challenging themselves. Rishi's outreach to elementary and high school students has helped foster greater interest in engineering from youth, and he serves as a committed steward of diversity and inclusion in the profession. In 2012, he was recognized by the Women in Engineering chapter at BCIT for his support.
The issue is also at the back end, having children between kindergarten and grade 12. We need to promote science and engineering at that level. So we need everybody. We need women at the undergrad level, but we also need women to go to grad school. We also need women to come back and be role models in the teaching profession and in the engineering profession.
Engineers and Geoscientists BC is proud to present its Teaching Award of Excellence to Dr. Rishi Gupta.
Hello, everyone. My name is Dr. Rishi Gupta. I work in the Department of Civil Engineering at the University of Victoria. First of all, I sincerely hope that all of you watching this video are keeping safe during the pandemic. The one project I'm extremely excited about at this moment is focused on coming up with a novel type of coating that can be applied on different surfaces so that the novel coronavirus cannot stick to these surfaces. The one application we have in mind is that for wash basins. We are hoping that these wash basins can be deployed at public places, especially at the entrances and exits of malls, of schools, of recreational facilities. And I hope by the time we finish this project, we can make Canadians a bit more safer than they are.
A very good evening, everyone. We, the CES Club of NIT Rourkela, in collaboration with ICE UK, NIT Rourkela chapter, bring to you a brand new session of CIVINAR, and I, Adarsh, am the coordinator for this third session of our very successful initiative where we welcome eminent personalities from different fields of civil engineering for highly intuitional webinars. Our previous sessions were graced by Dr. Nemi Bantia, who is the CEO of IC Impacts and Distinguished Professor of the University of British Columbia, and esteemed Professor Dr. Sriram Narasimhan of the University of Waterloo. But before starting today's webinar, first I would like to request Professor Shubhajit Mandal Sir, Associate Professor of our Institute and the Chief Patron of the Seminar Organizing Committee, to say a few words on today's auspicious event that we are glad to host. So please. Sir, can you unmute yourself kindly, sir? You're not audible. Thank you, sir.
Welcome, Professor Rishi Gupta. This seminar is our student initiative, though I am the faculty advisor, but they are taking care of all the things. Sincere thanks to all the students who are organizing this good initiative so that we can interact with our faculty worldwide. And also welcome to this session. I welcome Professor Gupta. Please you proceed. And I also ask our SHM club member to give the formal introductions to the Professor Rishi Gupta, and thereafter our session will start. Thank you.
Thank you, sir. So now we should proceed with the introduction, and we will start with Satyadeep, the club president.
Hello everyone, I am Satyadeep Mahapatra, President of SHM Club of NIT Rourkela and Chief Coordinator of today's event. I formally welcome Professor Rishi Gupta to the session. Thank you, others. You can continue.
Thank you very much. So today it is a matter of immense pleasure for us to be joined by Professor Rishi Gupta, Associate Professor of Civil Engineering at the highly prestigious University of Victoria, Canada. He's also the editorial board member of APEGBC, Head of Facility for Innovative Material and Infrastructural Monitoring, the FIMIM, plus a winner of the coveted REACH Award for his contribution in the field of undergraduate research-enriched teaching. With that, he is now working on a wash basin that will be resistant to COVID-19 causing novel coronavirus. Our earnest congratulations on that, sir. Now, in this session, he will be giving an insightful and detailed talk on the topic Sustainable Construction Technology and Structural Health Monitoring. We lay our warm and heartfelt welcome to you, sir. And here we can proceed with the webinar, sir.
So thank you very much. I hope all of you can hear me. And I'm going to share my slides. So Professor Mandal and all the executives, including Satyadeep from CEST, thank you for inviting me to join these eminent group of speakers that you just mentioned a few minutes ago. It's really an honor. And I take it you have most of the audience in India. So good evening to all of you. Perhaps you have a few people in a different time zone. Anybody from Canada, good morning to all of you. So with this, I will begin with the presentation. I don't want to keep it too long. I'll try and keep it to hopefully about 45 minutes. And the topic that I have for you is sustainable construction technologies and a little bit of structural health monitoring. So the acronym SHM stands for Structural Health Monitoring. What we will do here is take you through some of the topics on sustainable construction technologies. But before I begin, just wanted to chat about where I am located. And typically, I like to present this a couple of slides at the beginning of my presentation to say what exactly is the perception of Canada. So perhaps you think that there may be polar bears in my near vicinity. Perhaps think we have lots of igloos around. To a certain extent, this is true for northern communities of Canada. But what I wanted to highlight is Canada is also known for some very prominent civil engineering masterpieces. And all of you may know that the CN Tower was was actually the tallest building up until Burj Khalifa in Dubai took over. Um, Many of you may actually have heard about the Confederation Bridge. This is in Prince Edward Islands, and it's actually 13 kilometers long. Again, I think it's one of the masterpieces of civil engineering. We have lots of uh, important civil structures to brag about in Canada. And I wanted to give a quick snapshot of where we are located. So, of course, we share a pretty long border with the United States. And if I zoom into this a little bit, the University of Victoria is located in British Columbia, and we are actually at the southern tip of Vancouver Island. So that's the location of where we are. And with that little geographical mapping of UVic, I'll begin with the presentation. So I have a couple more slides to tell you a little bit more about University of Victoria. We'll get into what exactly is the need for innovative materials and sustainable construction technologies. Then I have three case studies that I have cherry-picked for the presentation today. One is on pervious concrete, or many people would call it porous concrete. One on rammed earth, and one is a SIP system, so a stay-in-place concrete forming system. And hopefully, if we have time, again, I want to try and keep this to about 45 minutes. If we have some time, I'll get into a little bit of non-destructive testing and a little bit on structural health monitoring. Again, let's talk a little bit about University of Victoria while I have the opportunity. So UVic is located in the capital of British Columbia, so in Victoria. We have roughly about 20,000 students on campus. And we have a very good graduate and undergraduate program. Within the engineering, we have several disciplines of engineering, but we of course have civil engineering actually included in the list as well. Civil engineering was actually one of the newest programs to be added at the University of Victoria. And while I have the opportunity, I want to recognize that we've actually had several NIT Rourkela students actually coming to Canada over the past few years. And they have come through the MyTax program. And I know that most of the students are very, very bright coming from NIT Rourkela. So thank you for considering UVic for your MyTax internships. I'll move on to the idea about why exactly do we need innovative materials and what exactly is the need for sustainable construction technologies. So we'll begin with just looking at what exactly is the state of Canadian and global infrastructure. So I'll show you some photographs. This particular one I really like because there was actually a lot of controversy behind why this bridge collapsed in Quebec, the province of Quebec, in 2006 in Canada. And the mystery behind this is the blame was laid on poor construction, the blame was laid on poor design, the blame was laid on a deterioration of the bridge, and so on. Then we have, many of you may have seen these photographs. This is the Minneapolis Bridge in 2007. There were quite a few people injured in this, 145 people. and 13 people died in this collapse. So these are very common sites that we see both in the news, we see it in the media, and closer to home for many of you is this particular bridge. The reason I picked this up is not because 45 people died, but this bridge apparently collapsed during construction. So we have a wide gamut of bridges from reinforced concrete, we got steel bridges, and then finally we have bridges that are actually collapsing even during construction. So we need to address some of these issues. Um, if you look at the financial side of things, many of my numbers are actually outdated. I don't expect you to read all of this, but I'll point your attention to one statistic here, that the infrastructure deficit in Canada alone for bridges is estimated at about $8 billion. I think this number has gone up over the years. But if in Canada we had to fix all the structurally deficient bridges, we would need about $8 to $10 billion to do that. So that's a pretty hefty number. I also have this statistic for India. This was the finance minister back in 2013, Mr. Chidambaram, and he had put a infrastructure deficit for India at $1 trillion. So these numbers are very staggering, and we as civil engineers, I think, need to think about, first of all, what's going wrong. Second, how do we find out what's wrong? And finally, third, how can we, in a very sustainable fashion, fix some of these issues? So with that, I want to move on to what exactly is the solution. And perhaps I'll quickly pause to see if everybody can hear me. Shubham or Satyadeep, can you just confirm you can see my screen?
Yes, it's fine.
Perfect.
What is the solution?
Perfect. Perfect. Thank you for checking in. So what exactly is the solution to solve some of these issues? So this particular slide is my interpretation of what infrastructure management should have, and some of the things that my lab actually does at UVic. So like was mentioned in the introduction, my facility is called a Facility for Innovative Materials and Infrastructure Monitoring. And these are some of the pieces that we handle in my lab. So we do a lot of work on developing sustainable composite materials, which includes fiber reinforced concrete and different technologies. We do a lot of work actually on condition assessment of structures. So again, you may have seen that in the introduction about use of drones, for example. So we completed a very large project a couple of years ago that involved both countries, India and Canada. And finally, we are doing a lot of work on smart sensors. So how can a sensor do more than one thing? So if there's the sensor measuring strain, in addition to strain, can it actually monitor anything else for us? So there are interactions between these. Many of you may have heard about the word LCA, many times referred to as LCC, so life cycle costing or life cycle assessment. And so we do a bit of work on this, not too much. And finally, where LCA and development of smart sensors interact would be called structural health monitoring of both new structures and repaired structures. So again, there's a light line showing different interactions. I won't spend too much of time. In today's topic, I will try and focus on sustainable construction technology. So that'll be the main focus of the presentation. If I have time, like we mentioned, we'll touch a little bit upon structural health monitoring as we move forward. So let's get into the main substance of the presentation today, and we'll talk about construction technologies. Like I mentioned before, I have three case studies that I cherry-picked for you. These are the three case studies where I was personally involved. I was personally leading these projects. So these are really close to my heart, and hopefully you'll find them valuable as well. So let's begin with the first one. This is Pervious concrete. Um, and I would like to begin with this photograph that I took a few years ago when I used to live in Vancouver. And I should try and explain first of all what's going on here. So this is a view outside my home. This photo was taken, I think, in February. So you can see a little bit of snow in my front yard. The tulips are trying to pop out, so that tells me it's end of February, early March. But what's going on in the background is you see the asphalt road. So, we as engineers and we as civil engineers, we love for things to be very neat and tidy and clean. So we, of course, love clean asphalt surfaces. What we have next to it is the shoulder, which has been compacted with the gravel has been compacted. So again, little bit of permeability, but not that much. And believe it or not, this little stream of water is actually the sidewalk. So this is where people would be walking, or bicyclists would be riding. But this, owing to the rain event, has become a little stream. And all of this water is going into the stormwater drain. And one of the astonishing points here is, I don't know how well this shows up on your screens, but this water has very high load of sediments. The turbidity is very high, the sediment load is very high. And this is a problem that we have created because back in the day, there would be lots of green here, lots of grass, lots of plants, and there would be a lot of ability for the landscape to absorb the water. So what we are doing now is we have increased the amount of runoff, and at the same time, we've made the quality of runoff very, very poor. So let's chat a little bit about this. What can we do? One of the solutions here is, what if we could have certain parts of, let's say, a parking lot, or even if you look at this photo in the back, what if you could have certain segments in the shoulder, perhaps, or even the main pavement of the asphalt? What if it was permeable, and could that change this runoff that's going into the stormwater drains? So this was the focus of this particular project that we were working on. Pervious concrete, also known as no fines concrete. It typically has between 15% to 30% voids. Since it is porous, it definitely will be lightweight. And we are talking about sustainability here. So if you're using 20 to 30% less material, of course, your material will also become sustainable at the same time. So these are some photographs showing different types of pervious concretes, anything from very sort of fine texture to something which is actually very, very, very coarse. So we'll talk a little bit more about this. The research questions that we were dealing with for this project was that the percolation capacity. So if I ask somebody, let me just go back to the previous slide. So these are standard products manufactured by different companies. If I ask someone and who's manufacturing this, they will talk about the percolation capacity of this product, and they may give you a number like 30,000 millimeters per hour of infiltration capacity, but they will not tell you what would happen if this pervious concrete was laid on top of, let's say, silty soil, or what if it was silt and clay mixed together. So one of the things that we have been working on is the percolation capacity should not be the capacity of just the pervious concrete. It needs to be site specific, and it actually needs to be for the entire system. So you cannot forget the subgrade where this material is being placed. Clogging is a major problem. So the photograph I showed you with a very high sediment load, if you have that kind of storm water going through a pervious concrete, your pores are going to block very, very quickly. Abrasion resistance is a problem. So because we don't have fines, the amount of paste is actually less in pervious concrete. And what that does, it actually can allow the aggregate particles to dislodge from the surface. And that particular phenomena is also known as raveling of concrete. So our site that we chose, we often laugh about this. That's not a typo. We call Vancouver Raincouver because typically there's the average rainfall is more than 1,000 millimeters per year. That's quite a lot of water that's actually coming on impermeable surfaces. So what we did was, this is a plan view of one parking lot. If I had to put a number, this would be something like 30 or 40,000 square feet, perhaps. And on this particular site, there were about 5 or 6 of such parking lots. So imagine the amount of rainfall, 1,000 millimeters in an year, that falls on this area, and everything is being diverted into stormwater drains. So what if we could change that? So we picked this little site here, was about 1,000 square feet. We picked this site because this was exposed to straight moving traffic. This was exposed to turning traffic, and it was actually exposed to the 3 stalls of standing traffic. And the idea behind this is the type of traffic, or whether the traffic is turning or not, can actually play a major role on the raveling of the aggregate. So if the tire is turning, the aggregates have a very big tendency to dislodge from the pavement. So this is the site that was selected. I'll show you some quick bunch of photographs. So I love the how fast this project was completed. So 12 inches of excavation that took place on site. What's happening here is a clear crush or gravel is being placed and is being compacted. So that was about 6 inches of the 12 inches. So this is completed compacted gravel on the 2 sides. And then what's happening here, this is my favorite slide, and this was something new that I learned about 7-8 years ago, was how do you compact and finish pervious concrete. So in this photograph, what you see here is actually not gravel. This is pervious concrete in a fresh form. And what's happening here is, this is a roller screed. And I should spend a minute or so explaining this. This is actually a hollow tube. It can be closed from the 2 ends, and it has handles to hold the 2 ends. And in the background, you can see this is motorized. So it's actually connected to a motor. And what ends up happening is, there's a gentleman holding this end of the screed. There's another person that holds the other end of the screed, and they turn on the roller, and this tube starts rotating, and the 2 people will drag this roller along to finish the pervious concrete. Depending on the compaction you need, what they do is they fill up the tube with a certain amount of water. So if you wanted more compaction and you wanted to make the screed heavy, they'll fill it up quickly with water, close the 2 ends, and do the same operation again. So this was very interesting, very fascinating. So in one operation, you get compaction, you actually get screeding, and you actually get some sort of a finish done at the same time. What's happening in the second video is, this is a smaller screed. So once you've done your longitudinal screeding, you actually bring a smaller one to get the kind of finish that you need on the surface. So very interesting. Then we left it for curing and misting for at least 14 days. I think in this particular site, we actually let it cure for a good 28 days because we had the luxury to keep it closed for that long. If this was an active roadway, you perhaps might not be able to have that luxury. So this is a cross section of how our pavement looked like. So that's your compacted 6 inches of subbase. There's your pervious concrete at top. If I were face to face and we had more time, I would ask this question to young budding civil engineers and say, when you see a cross section like this, what does this remind you of? And the one thing it reminds me of is filtration. So it reminds me of a different gradation of sand and aggregate being used for filtration. So you keep this thought in mind and think about what would happen if the runoff came through this media and then tried to enter groundwater. So you'd have a lot of contaminants like hydrocarbons from the vehicles that are standing on the parking lot. The hydrocarbons come from the gas, the diesel, and the different stuff that's actually coming out from the cars. Hydrocarbons can also come from asphalt itself, and this becomes the perfect filtration bed for stormwater. So this is the finished site. And as you can see, this actually blended very well with the rest of the asphalt, which actually was a great thing. So nobody could actually, sort of this pavement did not stand out, which was actually a good thing for the rest of the parking lot. So in this particular project, we focused on many different aspects. There was hydrological aspect, there was environmental aspect, and there was structural properties or material properties that we were interested in investigating. So I won't spend too much of time. We actually had a embedded pipe system here to monitor the amount of water that was being collected. We could use these pipes also to sample the water to see what was the quality of water. We did infiltration tests according to ASTM standards on this project. And here's a nice visual. You can see our site was on the downstream side, and you can see the runoff is coming from the top of the asphalt. It hit our pavement, and about 3/4 of the way, all the water is being absorbed. And what's interesting to notice here is this is not the stormwater that's being generated on the 1,000 square feet. This is actually the stormwater which is being generated on the rest of the parking lot. And this brings a very interesting concept of perhaps not having to do all the impermeable surface replaced with permeable surfaces. But what if you could have certain parts of your concrete pavements or certain parts of your asphalt pavements replaced with permeable surfaces? So that's a concept I would like to leave behind with all of you. We did some COD measurements on the project, and we did density measurements. You'll see that the compressive strength of these samples were rather low. The product that we were working with, we were expecting more like 10 MPa, but I attribute this issue to the fact that there was at the time no standard that spoke about how this should be cast. So, what level of compaction? How do you actually make this? Was an issue. So. But I think the low compressive strength is attributed to the fact that we did not know, or there was no standard explaining how cylinders should be made for porous concrete. We monitored the raveling. The good news was dislodging of aggregates did continue for the first month and a half. But after that, it significantly dropped, which actually was, again, a good sign for this project. So with that, I will move on, keeping an eye on time as well. I'll move on to the second case study, which is on rammed earth, or what we also call cement stabilized soil. So within the sustainability angle, I'm not sure how many have heard about this concept that was very popular a few years ago, called 100-mile diet. And the idea was, when we eat something, if we wanted things to be sustainable, if we ate things that grow within the 100-mile, I think was the radius, or I can't remember, maybe it was the diameter, we can be, our eating habits can be sustainable. So the same analogy applies to construction. If we can select materials which are not being hauled over very, very long distances, our construction methodology or our structures can actually be more sustainable. So use local, that can definitely make your construction practices more sustainable. So this is a photograph of construction happening in Tibet, and you can see what's happening here is there is basically soil in the background, and the people come together. It's usually a community effort. They take the soil, and you can see on top, this is of course a very labor intensive process. The soil is dumped into the forms, and you can see the height of the form is not that much, but they fill up the forms, and what they're doing is they're compacting the soil to make it nice and dense. So I call this a traditional form of construction. The walls are typically very, very thick. And the idea behind these very thick walls is because you can utilize the thermal mass of the wall for offsetting the heating and cooling during the day. So for example, outside in the night in Tibet may be very, very cold, but during the day, these very thick walls have actually absorbed a lot of heat. And what they'll end up doing is they'll start emitting the heat indoors, keeping the house warm. And the same phenomena is reversed during the mornings, where the outside starts heating up and the walls have actually cooled down over the night. So what I'm presenting to you today is not the traditional rammed earth. We call it the modern rammed earth, and I'm showing you two examples of applications in British Columbia. So this is the Van Dusen Garden in Vancouver. This is a house that I visited on Salt Spring Island in British Columbia. A very beautiful looking architecture, and uh, uh, just the aesthetics of this structures is just mind blowing in my opinion. So we were working with this material. One of the structural engineers came to us to say, when we are using rammed earth for walls, for example, we don't know what the bond strength is of the rebar. We don't know whether rammed earth should be treated as concrete. We don't know if rammed earth should be treated as masonry. So this is something that we were trying to answer, but I'll quickly back up a little bit to explain how we do modern day rammed earth construction. So we basically bring a compressor. This has anything between 60 to 100 psi of pressure. We connect it with hoses, and the other end of the hose actually goes to what we call rammers. So you see my collaborator here, Mirror, is holding this rammer. So the end of the rammer gets connected with the pneumatic hose, and when you turn on this rammer, this end of the rammer will be automized. So all you have to do is you just have to hold the rammer in place, but the other end of the rammer will be moving up and down very, very quickly. So this ends up semi-automizing rammed earth, because like you saw the construction in Tibet, you don't have to use manual rammers to compact the soil. So this is happening in my lab. We are making different samples here, and trying to understand the structural characteristics of rammed earth. Here is Gitanjali, one of my students, trying to find out what is the form pressure. So if I have rammed earth going inside, what would be the pressure on the formwork? So how do we design formwork for rammed earth? Here is some structural detailing. We were trying to understand how rammed earth will behave when we use loops, for example, in columns, or if we have diagonals being used for shear reinforcement. The one thing I forgot to mention for rammed earth is the way we do modern rammed earth is we put insulation in the center, and we have rammed earth on the two sides. So this end, exterior, would have rammed earth, and the interior would have rammed earth. So now you can actually benefit from the two aspects. You have insulated walls, and at the same time, you have walls which can offer you thermal mass at the same time. So again, I won't spend too much time. We actually constructed a mock wall We did a lot of non-destructive tests on this. I'll show you, if we have time, some photographs towards the end. So this is just a full wall that was constructed about 10 feet tall. You can see how this has the nice texture to it. And the reason for this beautiful texture is when this wall is within the forms, we usually put about 6 to 8 inches of wet material and we compact it down. Then we put another layer of 6 to 8 inches and we compact it down. So when this material is within the forms, you actually can't see it. And because you cannot see it, it actually gives you this natural, not very straight texture, which people love for architectural purposes. So I won't spend too much time. There's actually a out of plane bending test going on a rather full scale wall. This was done at my previous workplace, BCIT, and this was a very, very exciting project that we finished back then. So with this, I'll move on to my third case study, the last case study that I had planned for today. And again, time permitting, we'll let you, for those who are waiting for dinner, I'll let you all go. I usually end up being in such awkward situations where I'm always presenting at conferences where I'm the presenter between lunch and all the audiences. So audiences hate me to say, can you please finish very
So
quickly?
it's fine for us now, sir.
Okay.
Yes, Professor, you can take your
Okay,
time, no
that's
issue.
great.
Yes, sir. There's no issue.
There are many students, they are very interested. Your work is very nice. What I see, Pervious concrete. Actually, I will try to
Absolutely.
discuss
Thank
with
you.
you at
Thank
the
you. I'm
end.
glad you're liking it. So I'll
Yeah,
continue with my
please.
third case study.
Yes,
So you
sure.
may have heard about stay in place forming system. So I should just explain this a little bit more. So the idea behind stay in place forming system is you erect the formwork. It Typical formworks are made out of timber or wood. In India, we use a lot of steel, for example. And the idea for stay in place system would actually be that you don't remove your forms. The forms actually become a part of the structure. This type of stay in place is very popular for bridge structures, where if you're building a caisson, for example, you leave the structure in place and the piers come in the center of a caisson. In Canada, one example of stay in place is um, what we call insulated concrete forms. So it's called ICF. And the idea is for even for residential construction, we put foam on the two sides. It ends up becoming the formwork for concrete, but we don't remove the foam. So the foam ends up becoming the insulation for the concrete walls. And that system is quite popular. What I'm showing you here is actually a very unique PVC system. And the reason I'm privy to this case study is I used to work for a company in Vancouver as the director of research. The name of the company is Octoform Systems, and they produce these stay in place systems. And I'd show you what's going on here. So the PVC system comes in different components. So there are thin panels that you can see here. There are connectors that you can see this gentleman on site trying to install. And what you do here is you have a series of panels. You attach connectors to this, and you put another set of panels on the outside. So you keep building this formwork assembly on site. It gets shipped in flats, so it doesn't cost more. And then you install this on site. And once your, for the lack of better word, your box is ready here vertically, you pour or place concrete in the form. You can see the height of these walls. So these can be very massive structures. And what would end up happening is after you pour concrete, this will become the finish of your. So this is just a formwork sitting on the ground. It actually will be tilted up, erected up, but what will end up happening for walls is inside and outside of the wall will be a PVC finish. So for certain applications, they love this because you never have to paint your walls again. PVC is a very durable material, as we know, and PVC can be cleaned very, very quickly. So again, just to back up a little bit, the applications for this PVC forming system is widespread. It could be used for car wash structures. It could be used for commercial buildings, as you can see here. And what's actually happening here, I don't know if you can notice it, but this is actually a round tank. You see how this is curving on the sides. Constructing this with any other material would be very challenging. So imagine constructing a tank and you have to use steel plates to get the very uniform curvature. Would be very difficult. Same thing with plywood, for example. To get a very uniform curvature would actually be very difficult. So because it's made out of PVC, there's a little bit of a stretch to the component. So you can actually align it along with your scaffolding, and you can get whatever shapes you want. There are examples of small tanks being done for aquaculture, and those tanks, I believe, were were very small, were 15 to 20 feet in diameter. So very, very high curvature on those tanks, but those were done using this PVC system. So why we were involved in this project was Octaform wanted to understand what happens when I have concrete and steel. You still use steel in these structures. What happens to the structural capacity of concrete, which is now encapsulated in PVC? So this is a plan view. What we were doing in in our lab was we had different configurations of PVC. So you can see that there's the white panel. Here is another panel. Here is a connector and the whole assembly. So different types of systems. We did different heights of columns, and we placed concrete in this, and then we took it to the next level. So you can see, I think our tallest column, I have it on my next slide, was about, I think it was about 6 to 9 feet tall. So what you can see is the concrete is encapsulated completely in PVC, and we tested it for pure axial capacity. And what we found here was so we had anything from 20-inch height of the columns to 72-inch height of the columns. So if you look at that, this has been normalized or is being compared to control concrete. So your control concrete is here. So what that means is if your control concrete had this compressive strength along the horizontal axis, all the other systems that were PVC encapsulated had, let's say, 20% more or 5% more or 10% more than control concrete. So with the exception of one configuration, and we attributed this to some issues with testing, all the other columns had a higher structural capacity as compared to control. So this was actually a little bit exciting, actually very exciting, but at the same time, it was the idea that a very low modulus PVC. So PVC has an elastic modulus of, let's say, 5 GPa or less. Your concrete has an elastic modulus of 30 GPa. And the idea that something which is so low modulus can actually give you confinement and have increase in your strength was truly astonishing. So we don't have much time, but there were other reasons that we believe attributed to the high strength. Maybe I should quickly mention. We also attributed to the fact that because the concrete was completely encased in PVC, the moisture did not evaporate very quickly from concrete. So very good hydration actually, or complete hydration could take place within those columns. So truly interesting results. I think you're going to like the next slide that I have, which is actually a little bit more graphic. So I call this secondary benefit. And these are the examples of 2 columns. So this is your traditional column, normal concrete, no PVC, no formwork, nothing. This has been tested in compression already, and you see the amount of concrete loss that has taken place, which is expected. Nothing wrong with that. The column next to it, same height, actually has been also tested in compression. So this has failed. If I load it again, the load capacity is not going to go up. It's going to be a very flat curve. But what's very astonishing here is this tested column has no loss of concrete because everything is encapsulated within the PVC. Now, the reason this excites me a lot is because you think about seismic applications, you think about impact applications, you think about blast, for example. And what would happen if this is just a column, but you would have a wall. So another panel here, another panel here, and this would become a long wall. So some of these ideas were very interesting. For example, for the US Air Force in Florida. And what they were thinking about was what if this concept could be used for making bunkers, for example, for soldiers. So soldiers, if there's a blast that happens on the outside, the structure may fail, but there'll be no pieces of concrete actually that falls on the soldiers that are inside the bunker. So very interesting. And so that this particular slide was the end of my 3 case studies. And if I may quickly do another 5-10 minutes, I can cover some of the structural health monitoring aspects.
Yeah, no issue, Professor. You can
Okay.
continue.
Okay, that's great. So I'll move on to structural health monitoring. So SHM, I'll use this acronym a few times. And then we have non-destructive testing, or NDTs. So the reason I have included this in my sustainability presentation is by using structural health monitoring or non-destructive testing, we can actually extend the life of our structures. So if you have a bridge that has been in service for 50, 60, 70 years, and you don't know how long it's going to last, that's a problem. If somebody comes and says, hey, I think this is beyond the design life, we should decommission this bridge. But what if somebody could go in and truly find out the condition of that bridge and say, you know what, you actually have another 15 years left in the structure. So that to me is sustainability, because you have deferred the need for reconstruction. You have deferred the need for use of new materials, and you've actually extended the life of the materials by a certain amount of time. So that to me is actually going to be the future for several years to come, where we truly need to be safe, but at the same time we need to get more out of our structures. So these are just some I won't get into the very specifics, but hopefully you'll have an appreciation of some of the techniques. I'll show you a couple of projects that I was involved in. So this is during my time at the University of British Columbia. So there are 2 projects that wanted to show you. So this is a project where we had half of the slab was no fibers. The other half was actually fiber reinforced concrete, where cellulose fibers were being used. And we were monitoring using embedded sensors. So what you see here is embedded strain gauges that were placed at strategic points. We were interested actually in finding out the plastic shrinkage that takes place during the first few days in the pavement. This is back in the day. This is almost about 10 to 15 years old. This is how our wireless system used to look like back then. And this was a major accomplishment about 15 years ago. Not anymore. And now you have your little Raspberry Pis that can actually do a lot of computation for you. But this is how our systems looked like several years ago. One other project that we did, this was a loading dock. So this is a plan view of a loading dock, and we tried different combinations here. But the one combination I think is very interesting is a joint-free slab. So many of you may know this, that whenever we make a concrete slab, if it's being used as a pavement, for example, we usually like to have a saw cut. So we cut our slabs into smaller pieces. So the shrinkage and thermal expansion is easy. And if I don't have this saw cut, then because of the thermal expansion and contraction, you'll have large cracks happening. But what we wanted to see was, would it be possible to have a slab which is more than 6 meters long without a joint, but have fiber reinforcement in it? So again, some photographs of construction. We used polypropylene fibers, a hybrid combination here. We had some fiber optic sensors that we used on this project in addition to electrical sensors. And we used a whole suite of NDTs, Schmidt hammer or rebound hammer, ultrasonic pulse velocity, electrical resistivity. We were measuring corrosion on this project. And what I wanted to show you was, this is just one example of using NDTs. So if you take this plan view, this particular slab is this, and the joint-free slab is actually right here. So you can see that the small slab and the joint-free slab had very similar results. So this joint-free slab and this had very similar result. Again, I have not put the details of the NDT, but the results were very similar in the 2 or 3 NDTs that we use. So this was very promising to see that if fiber reinforced concrete was used, you could perhaps have longer slabs which are joint free. So I'll take maybe 2-3 more minutes and then start wrapping this up. So damage detection is something that I wanted to mention. So this is a project that was funded by India Canada Impacts, IC Impacts. You mentioned Dr. Banthia was one of your speakers, and I know he presented details of IC Impacts. So this was a project that was completed a couple of years ago. And the idea here was to use drones for condition assessment of different structures. Again, just 2-3 more slides to show you some photographs. So what you can see here is outside my lab, we have a simulated slab, and a drone is actually being used to find out the condition of the slab here. That's my co-PI, Dr. Bala Subramaniam from Welltech University, who was visiting us during this project, and our student team here who worked on this project. I won't go into the details, but different instrumentation being used here on our simulated slabs. So we've done a lot of work where we actually take slabs and we install defects at certain known locations, and then we use non-destructive tests to find out whether first we can detect those defects or not, and second, how accurately we can actually detect those defects. So we've done some work using infrared cameras as well, and a whole suite of NDTs that we have used. So again, keeping an eye on the time, I would like to acknowledge all the grad students. My presentation looks, if it looks good, it's attributed only to all the hard work of all the students that have contributed, all the grad students, all the undergrad students from University of Victoria, from UBC, even from BCIT, and like I mentioned, some of the international students that may have come from different parts of India and elsewhere who have contributed to these presentations. So quick acknowledgement to Octaform for the PVC project. The Rammed Earth project was sponsored by Cement Association of Canada, and of course NSERC is our large contributor. The drone project was sponsored by IC Impacts, and so with that, I finally want to thank CEST, all the wonderful executives. I think you are doing a great job running a very professional seminar series. in particular Satyadeep, the president of CEST, and all the other members of executive, Professor Mandal as well. Thank you for having me for this presentation. And finally, thank you to all of you, the audience who were listening in into this presentation today. So there's my contact email if anybody had any specific questions. Many of the case studies that I presented are available in open access papers. But if there's anything particular that caught your interest and you wanted more details, you can find me on ResearchGate, and I'll be happy to share some of those papers that were presented today. So with that, thank you to all of you for your attention.
Sir, should we have a short question and answer session?
Absolutely, no problem.
Yes, sir. We'll start.
Thank you. Thank you, Professor.
Thank you.
Just a minute, let me. Thanks, Professor. Thank you, Professor Gupta, for a wonderful presentation. I think that your work is very basically interesting, and that your first presentation, the Pervious concrete. So, is there you are using any admixture there for the Pervious concrete?
Right. So, Professor Myrtle, that's a very good question. So, the product that we used was actually made by a company,
Okay.
and so it was a proprietary material. And what we wanted to do was we wanted to push the boundaries. So, the company was very comfortable using the porous concrete on sidewalks and bicycle pathways. But
Okay.
we said no. We want you to use it as a pavement material. So, but I know that they are using an admixture, which actually allows the material to have whatever workability it has right now, because apparently the water content in the pervious concrete is quite low, because they're always struggling to get the compressive strength. So they
Yeah.
do have an admixture, but I don't know the details of that actually.
So one more question. I was wondering, the durability aspect, is there still left, or you are also conducting the durability, that how much time it will sustain?
Absolutely, that's a very good question. One of the biggest things for us is actually the freeze thaw damage.
Yes.
So if my pavement is saturated with water, and then if the temperature drops to sub-zero
Yes.
overnight, it's gonna
Yes.
blow the
Yeah.
whole pavement. But for about the 5 years that we monitored the pavement, it went through several cycles of freezing and thawing, natural cycles, and we didn't see any more raveling. We didn't see any more spalling actually taking place. So that was a good sign actually.
Actually, so one of my student is working on concrete. I said normally I work on the dynamics and composite, that FRP composite. But I took one student, Mr. Maji. He is working on concrete and geopolymer. You are talking about. He also basically in first year of the PhD. So I hope he probably in the next future he may contact you to get some guidelines from you.
Sure. Yeah, no problem.
And one more question, that you are talking about, that your PVC concrete there. So, is there any role of that surface roughness of the PVC coating, with that you are getting some sort of your confinement effect? If you have to see that, I think that surface smoothness of the PVC coating. If it is rough, probably it may give more confined effect. I don't know. Probably it may give some more effect.
That's also a very valid point. And the reason why we were a little bit astonished was the back side of the PVC, which is in
Okay.
contact with concrete, is actually very
Yes.
smooth. But
Okay.
what ends up happening is when you have the panels and the connectors,
Yes.
and you place concrete in the center, it actually exerts a pressure on the whole PVC system.
Yes.
So it's more of a mechanical confinement than a perfect bonding. But you're
Bonding.
absolutely right. Absolutely right. Yeah.
Okay, let other students ask some questions. Okay, hopefully they are very interested about the research. Personally, what I thought your research is very nice. In the 2-3 topic what I just gone through, I also get some interest to work on that. One is that you're talking about for the army. that if the confinement is there, that concrete not fall. I am also thinking to write some project proposal, so I'll let you know once I complete something. I'll send you.
Absolutely.
Okay. Okay.
Absolutely.
Thank you. This
Yeah.
others. Uh, I'm done. Okay. You ask other
Yes, sir.
student and just take other questions. Okay.
Yes, sir. So our first question is by Nishan Bhatta. So unlike bitumen, concrete will produce thermal cracking. What is the procedure to counter that?
So this is concrete. Like I was mentioning in my presentation, one of the standard protocols for concrete is, we know it's going to have thermal expansion. So rather than preventing the thermal expansion, we let concrete do what it needs to do, and that's why we usually limit the size of the concrete base. So if you drive over bridges, for example, or concrete highways, you'll see that when you're driving, every 3 meters or so you hear a slight thump. So it goes thump 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 thump. The reason for that is we always divide concrete into bays. If you, like I mentioned in my case study, what we were looking at was, if we did not divide the concrete into small bays, would it still crack? And the example that I showed you was actually more than 6 meters in length, and it was actually being used as a loading bay. So the loading was actually quite heavy on that. So my quick answer is, don't prevent thermal expansion, but the thermal cracking can be prevented by limiting the size. And second one, my favorite actually, is fiber reinforced concrete. Fiber reinforced concrete for plastic shrinkage, fiber reinforced concrete for drying shrinkage, and fiber reinforced concrete for reducing thermal cracking. Very, very effective.
Moving on with the next question, we have this question from Havisha. It is common belief that green buildings cost more, and so many people do not opt for it. What is your opinion on that, sir?
So that's a good question. So if I may take the example of a rammed earth, for example, the modern day rammed earth, definitely it costs more than traditional construction. The reason for that, at least for rammed earth, is we are trying to use rammed earth where there is a lot of timber available. So the reason all the houses that I look around me are made out of wood here in Canada and in Victoria and in BC is because we have a lot of timber here. So it may not make sense for me to use something other than timber, even though we have a lot of masonry, lot of concrete. So where I was going with this is, there are certain regions and certain situations where green construction makes a lot of sense. So for example, I'm in Tibet, and I'm just giving you an example of Tibet. It could be a very remote community where you don't have access to good sand. And people tell me, actually, in Gujarat, it's a big problem for sand. So there is no good sand available. For example, you may have difficulties in accessing coarse aggregates. So in that context, in a very remote community, rather than hauling this material and sand 1,000 kilometers, using local materials would make a lot of sense. So where I'm going with this is, green buildings may cost more if you try and force it, but there are certain unique situations where green buildings make a lot of sense. uh, I'll quickly add one more thing. My favorite here is, uh, in trying to make green concrete, or green structures or green buildings, we forget that the building needs to serve its purpose. So what good is a building which is green and sustainable, but when you go on a December day, it's so cold inside because you have used this new sustainable way of heating your building, that the comfort level in the building has gone down. So my long answer to your question is, uh, green building choice needs to be dependent on the location. One idea of a green building cannot be applied everywhere. So we just have to be selective.
Moving on to the next question. This is by Suprapriyadashini. What is the increase in cost factor from traditional rammed earth to the modern one? And is it affordable for the general public?
So, Shubhra, the answer is no. It's not cheap. It's actually more expensive than traditional construction. But again, I go back to the same idea of the example that I gave of Tibet construction, right? So, depending on the location, it makes sense. The modern rammed earth, the examples that I showed you, the people why they're using it in Canada is they love the architecture. The finish of those structures is just amazing. So people are paying extra cost just to have that unique looking house. Uh, my industry sponsor would tell you that if you make that expensive house out of rammed earth, over the life of your rammed earth, you will actually have enough savings from your electricity bill or heating bill to pay for it. I'm not 100% on that, but at the moment in Canada, it's in my opinion, it's being used because it just looks amazing.
So we have next question from Subham Das. How can we increase the use of recycled and bio-used materials?
Shubham, that's also a good question. My personal opinion is sort of, I think there's a theme emerging here that we don't want to force the use of recycled materials, because if you look at literature, if you look at real examples, if you take an example of recycled concrete, for example, the use of recycled concrete as aggregate more often than never will reduce your compressive strength, right? We know that. And to just because we need to recycle concrete, if your life of your new structure is going to be compromised, I personally think it's not a good idea. Having said this, in Canada, for example, the concrete from old structures is crushed, and the application where they use all of that is as a sub base. So let's say you're laying your pipelines and you need that sub base underneath. Let's say you're doing a pavement and you need your crushed gravel that I showed you in my slides. Those are perfect examples. It's not per se structural concrete, and those are good examples. For your bio-based materials, I my suggestion is the same. I think there are lots of examples of uh, you know uh, uh, natural fibers being used in asphalt, natural fibers being used in concrete. I think they all make sense, but at the end of the day, we need to think about the durability. If by addition of cellulose fibers or by addition of hemp based fibers, your life of your concrete will be compromised, then in my opinion, it's actually not a very good idea to use it.
Sir, our next question is by Chaitanya Kumar. How much skid resistant do pervious concrete roads offer?
Chaitanya, they probably have too much skid resistance. So if you look at the surface of pervious concrete, the texture is very rough. And the reason I say too much skid resistance is there's a little story here that when we were doing the project in Vancouver of pervious concrete, and I showed them examples of pervious concrete which had very rough texture. They said, what would happen if I have a snow cleaning device? So you know how they clean very long parking lots when it snows, they have like a truck with a blade at the bottom. And what the blade does, blade goes and scrapes the top surface of the asphalt. So they were concerned that if your surface is so rough, what if the blade catches the top surface and starts removing all the aggregates? So long answer short, it probably has uh, um, um, enough skid resistance for sure, perhaps more than what you need actually.
So should we take more questions?
Absolutely. I'm okay for the next 5-10 minutes for sure. Yeah.
Okay. So next question is by Bishwajit Sahu. How will the economical aspect uh, differ if we use PVC covering instead of paints?
That's a very, very good question. Like was asked before about rammed earth construction, PVC use as a formwork will be expensive. So if you say I'm using PVC because I need a forming system, that's an expensive proposition. But what Biswajit has asked, that's a very good question. Now, if I assume that my PVC system is a finished system, and I never have to paint my building again for the next 50 years. Now that's when things start paying off. So you're absolutely right. I cannot give you a immediate answer, but you think about examples like car wash stations. So car wash stations get beaten up every day by water, soap, whatever. So if I cannot make it out of wood because that's going to rot very quickly. If I make it out of masonry or traditional concrete, there's actually a lot of mold that starts growing on the surface. PVC is wonderful. I let it go through the cycles. Once every 6 months or once every year, I take a power wash and just wash the surface. So all the mold, the grime, whatever is on the surface just gets washed off. So it's a very good question. Many people love it because of the cleanability or the need for not to paint actually.
So our next question is by Arman Devkhan. If we take the case of Indian market, will a common brick walled house be more effective or the rammed earth wall be cheaper and strong enough?
Armandev, this is a very good question, and my little experience takes me to Indonesia after the big tsunami in 2004/5. So I was in Indonesia in a place called Medan, and after the tsunami, when I visited, it was already 2-3 months after the tsunami, and the tsunami, of course, had triggers of earthquake, as you know, prior and after. They had 2 or 3 soccer field of rubble from broken houses that was laid, and it was a sight was very distressing actually, and all that rubble was actually from masonry. So the most damage that took place in the seismic event, unfortunately, was with masonry construction. One, they were probably not constructed properly. You got 12 feet of masonry with no lintels in between, no reinforced frame in between, and all of those walls, the 12, 14 feet of walls, everything fell down. So if I compare rammed earth with brick wall construction, I think rammed earth would be more of a structural wall. It could be if you design it properly, as opposed to a traditional brick wall. The good news here for comparison is I usually say rammed earth is not a good thing because it's very labor intensive. But your example is perfect because brick wall is very labor intensive too. So the amount of time it takes for a mason to lay the bricks, I think rammed earth could be actually faster. So I never thought of this comparison, but I really like it. So my long question short is because in India we have good access to labor, and the costs for labor are not that high as compared to the Western world. It actually, I haven't done this analysis, but actually would make good sense to consider rammed earth for construction. And I didn't add the fact on the last question that on masonry, then you need to plaster it. So you're going to plaster it on the inside, you're going to plaster it on the outside. Very, very time consuming. In rammed earth, once you strip your forms, you'll have the beautiful architecture. In rammed earth, they also put pigments. So you saw some of those colors. So you can have little reddish tinge, you can have brown, black, whatever. Yeah.
So our next question is by Rishabh Bajaj. Does the efficiency of pervious concrete pavement reduce over time in terms of the capacity to allow water to pass through?
Good evening, Rishabh. long time. So thank you, Rishabh, for asking. So Rishabh was one of our prime examples of a student from NIT Rourkela who actually came to UVic and did his MyTax internship successfully. So congratulations, Rishabh, and thank you for joining us. We should chat offline some of the time, but you're absolutely right. The efficiency of a pervious concrete will reduce over a period of time. It's a big issue, and some people will say that if you have a big stormwater discharge with very high sediment loads, it'll block your pores in pervious concrete. So it is definitely an issue. There are a couple of maintenance protocols that are in place where every year the design standards suggest that you go and power wash the surface. But there's an issue with power washing. It may remove the sediments in the top layer, but at the same time, it pushes some of the sediments even deeper into the pavement. So that is an issue, ongoing issue for sure.
So with this, we have addressed most of our questions, our important questions, and now it's time for us to invite Shubham Das, the organizing secretary of CIVINAR, to deliver the vote of thanks.
Hello everyone, myself Shubham Das. I am a pre-final undergraduate from the Department of Civil Engineering of NIT Rourkela, and I am one of the organizing secretaries of the event CIVINAR. Let me start by just saying how grateful we are towards Mr. Rishi Gupta for taking his precious time and such effort to deliver his webinar on sustainable construction technologies. His contribution in the structural health monitoring of structures with integrated UAV and image processing system is commendable. And he has also been working on projects to develop coronavirus repellent surface such as washbasins, which is a remarkable innovation. He also helped us understand how certain new technologies in construction field help in preserving and protecting the natural resources while utilizing energy, water, and other entities efficiently. He also proves and demonstrates how engineers can leave their marks in variety of fields with their innovations only. I am sure everything you told us today will be of great use to us in some day. Now I would like to thank Professor Subhajit Mandal, the faculty advisor of SEST Club, whose constant guiding presence has been and will be indispensable for us. I would also like to thank NITR and SAC for giving us this chance and such constant encouragements to do such events which help us grow and develop. And of course, the webinar would not be complete without its lovely audience. Thus, I would like to thank you all for attending and making it a success. And last but not the least, I would like to thank the organizing team for this event who put tireless hours into making this event possible and seeing it through. And thank you all for turning up for the session. We hope all of you are keeping safe and doing well. We will have more such interesting sessions in the upcoming days. So stay tuned. The video links of our previous sessions are provided in the description. You can go through that and don't forget to subscribe our channel. Take care.